So far, we have described how to determine where a function is increasing or decreasing by analyzing its first derivative. So today, we'll obtain more details regarding the shape of the graph of a function by discussing its concavity. So we begin with a function f that is defined on the open interval I equal to AB. So we say that the graph of f is, on the one hand, concave up on the interval I, if and only if the graph of f lies above its tangent line at x, f of x, for each number x in I. So a picture is given here of a curve where notice that at any point along the curve on the interval I, when we look at the tangent line at the point, the graph remains always above the tangent line. Thus, this curve is concave up on the interval I. We also say in such case, if a function is concave up on the interval, it's sometimes also referred to as being convex on that interval. So we could also have the graph of f be concave down on the open interval I equal to AB. So that would occur if the graph of f lies below its tangent line at the point x f of x for each number x in I. So observe that in the second picture, at any point on the interval I, the graph of f always remains below its tangent line at the given point. Thus, the graph of f in this case would be concave down. So a function that's concave down on the interval is sometimes just referred to as being concave on that interval. So you might see the word convex substituted for concave up, or concave substituted for concave down in certain texts. We have an important concavity theorem that allows us to determine, based on derivative analysis, whether the function is concave up or concave down. So the theorem simply says that if our function f is differentiable on the open interval I, then f in fact is concave up on that interval if and only if the first derivative f prime is increasing on I. However, f would be concave down on I if and only if its first derivative was decreasing on I. So going back to our two pictures, we could see in the first case, we have the first derivative function, right, which is the slope function. First picture is increasing on the interval I, right? The first derivative starts out negative, becomes 0 at some point, and then becomes positive. It's increasing as we range over the interval I. However, in the case of the second picture, we have a situation where the first derivative is initially positive, becomes 0, and then becomes negative and more negative as x ranges over the interval I. So clearly, the first derivative function, the slope function, is decreasing in the second case, and that condition makes the graph of f curve downward, whereas in the first case, where the slope function, the first derivative function, was increasing on the interval, makes the function curve upward. So the condition of concavity is directly related to whether the first derivative function is increasing or decreasing on the given interval I. Okay, and so now we have a definition for the second derivative of a function. We say that if y is f of x, its second derivative with respect to x could be denoted by any of the following. Okay, simply in the prime notation, the Lagrange notation, we would write y double prime for the derivative of y prime, or the second derivative of y. Or similarly, the same reasoning, we write f double prime x to be the first derivative of f prime at x. Okay, again, the prime or Lagrange notation. We have Leibniz notation for second derivative as well. So we write d squared y dx squared to be the derivative with respect to x of dy dx, or the second derivative of y with respect to x. Notice that in the notation, the superscript 2 appears between the d and y in the numerator, whereas it appears after the x in the sort of denominator, okay, of the expression, so to speak. And maybe I think the reasoning being that, here you have, two d's here on top, so thus d squared, where on the bottom you have dx, so like dx squared. But in any case, the derivative of f with respect to x in the derivative of f with respect to x, rather, in the Leibniz notation would be written d squared f dx squared. So this is our notation for second derivative of a function, okay, which is simply the derivative of the first derivative would be our second derivative. So we have a very simple test to determine whether a function is concave up or concave down on an interval. We call it our concavity test. So assuming that our function f is twice differentiable on an open interval I, okay, so the second derivative exists at every point of that interval I. So in such case, if the second derivative is always positive on that open interval, then that means, right, the first derivative function is an increasing function on I, right? Because the second derivative is the first derivative of f prime. And we know that if a function has a positive derivative on the interval, it must be increasing, right? So positive second derivative means our first derivative function is increasing. But remember, by our concavity theorem, if the first derivative function is increasing, then f is indeed concave up on the interval. On the other hand, if our second derivative is always negative on the interval I, then it follows that the first derivative function is a decreasing function on I. So that implies that, right, the first derivative function is decreasing, f itself must be concave down. So a very simple test for concavity, if the second derivative is always positive on the interval, our function's concave up. The second derivative is always negative on the interval, the function's concave down on that interval. Okay, so now let's apply that analysis to the graph of a particular function f. Okay, so they say to analyze the monotonicity and concavity of the graph of this function and specify its extreme points. Now, monotonicity is kind of a fancy word to say where is the function increasing or decreasing on the interval. Okay, so we look at this function f, it's defined over the entire real line, and we say, well, could we see any intervals on which its graph is increasing, right? So as we move from left to right, where is the height increasing? And so clearly, if we start at A, right, and we go up to C, clearly on that interval from A to C inclusive, the function's always rising, right? Where is the function decreasing? Well, you could see from all the way sort of from minus infinity to A, right, the graph was always going downward, right? It was decreasing. And similarly, starting at this value C and going to the right, the function's graph is always going down. F is always decreasing. So it's decreasing on two intervals, minus infinity to A and C infinity. it's increasing between A and C. Regarding the concavity of the function, we notice that it's curving up from all the way from minus infinity to B, right? The graph of f is always going to be above its tangent lines, right? It's curving upward over the interval from minus infinity to B. Where else does it curve up? Well, we see between D and E, okay, between D and E, the graph would be above its tangent line at any point of the interval DE. So it's concave up on two intervals. It's concave down, right? The graph curves down. It's below its tangent line at any point between B and D, and also at any point from E to infinity to the right of E. So it's concave down from B to D and from E to infinity, concave up from minus infinity to B and from D to E. Regarding extreme points for the graph of this function, we see that, well, certainly there's a high point here when x is c, right? So the value of f at c is going to be our relative maximum value, and then the ordered pair cf of c, we would call that a relative maximum point for the function. As far as relative minimums, we see there's a valley in the graph, right, at the point A. So f of A is a relative minimum value, and the ordered pair AF of A we would call the relative minimum point. As far as absolute extreme values, well, we can see there actually are none, because the graph indicates that as we move, further and further in the negative x direction, the graph is going to continue to rise to be unbounded above. And similarly, as we move further and further to the right of E, the graph is going to continue to fall, and so it's going to be unbounded below. So the range of this function would be all real numbers, and therefore there would be no absolute extreme values for this particular function. So you could see how knowing the concavity of the function gives us a little more detail about how the shape of the graph must appear. And one other point we're interested in is points where the concavity of the graph changes. Okay, so specifically, we would call the point CF of C a point of inflection, or simply an inflection point for the graph of f, if f does indeed have a tangent line to its graph at the point CF of C, and there's a positive number delta, so the graph of f is concave in one sense on the left of the point C, say on the interval from C minus delta to C, and then concave in the opposite sense on the interval from C to C plus delta. And geometrically, we know that the graph of a function crosses the graph of the tangent line at the point CF of C if that point is in fact an inflection point for the graph of the function. So specifically, like looking at this picture in the figure, we see that initially on this interval on the left side of C, the graph curves downward, right? It's concave down. You can see how the graph lies below its tangent lines. However, when we pass to the right of C, okay, then the graph curves upward. Now its graph is above its tangent lines on the right side of the point P, which is CF of C. And you could see that when we draw in, okay, the tangent line at P, okay, that it actually cuts through the graph of the curve, right? Where on the left side, the curve is below that tangent line. On the right side, it's above the tangent line. So at the inflection point, the graph of f will cross the graph of its tangent line. The other thing that we notice in this particular picture is that we see, and we would just do a little analysis of the first derivative function, which is, of course, the slope function. Well, we see that, it starts out positive valued, right? Becomes 0, then becomes negative. Then you could see you have the most negative slope to the graph occurring at the point C, f of C, right, where it's steepest decline, okay, of the graph, and then it becomes less, steep in the negative sense, right? We ultimately here have a 0 slope at this point, and then the slope becomes positive. So you see, you started out with a positive slope, becomes negative, becomes most negative at the point when x is c, then becomes less negative, and then becomes positive again. So our first derivative function, right, the slope function, is minimized at x equals to c. So therefore, the first derivative function, right, the slope function, has a relative minimum value at x equals c, which means that its derivative, right, the derivative of the slope function, the derivative of f prime, or in other words, the second derivative of f, must be 0 at x equals c, since at c, the first derivative function is minimized. Okay, and that's basically the gist of this last theorem on concavity, that simply says if our function f is indeed twice differentiable on the open interval I, right, that the first and second derivative, they exist at every point of the interval, and moreover, the point c f of c is indeed a point of inflection for the graph of f, then necessarily the second derivative of f at c must be 0, just like we analyze in this picture where the second derivative of f at the inflection point had to be 0. And so you're free to read through our analysis, which is just a sort of slightly more general version of what we argued for this picture. But these then are our major theorems dealing with the concavity of a function. And in our next video, we'll apply this analysis to a curve sketching problem. So thanks for watching. We'll see you next time. Goodbye.